Welcome to Jeremy's IT Lab. This is a free complete course for the CCNA. If you like these videos, please subscribe to follow along with the series. Also, please like and leave a comment, and share the video to help spread this free series of videos. Thanks for your help. In this video, we will return to Layer 3, after spending quite a while in Layer 2 studying VLANs, DTP, VTP, spanning tree, and Ether channel. This video will start a series of videos on dynamic routing. Dynamic routing is in contrast to static routing, which we covered in Day 11 of this course. Static routing involves manually configuring routes to each destination with the iproute command. Dynamic routing, on the other hand, involves configuring a dynamic routing protocol on the router, and then letting the router take care of finding the best routes to destination networks. It's called dynamic routing because it's not fixed. If you add a new LAN, routers will automatically inform each other about how to get to that new destination network. If one path to a destination becomes unavailable, the routers will automatically start using the next best path. Over these next few videos, we're going to cover a large portion of the exam topics list. 3.0 IP connectivity accounts for 25% of the CCNA exam, and we're going to cover almost all of it, just leaving out 3.5 for later. We've already covered some of the topics in here. For example, we've covered parts of 3.1, 3.2, and 3.3. My plan is to review some parts we missed from here, and give a general overview of dynamic routing protocols in today's video. Give an overview of two routing protocols, RIP and EIGRP, in Day 25, and then spend another 2 or 3 days to cover OSPF, which is actually the only dynamic routing protocol mentioned in the exam topics list, in 3.4. However, even though OSPF is the only one mentioned, you still need a basic understanding of other dynamic routing protocols, and need to be able to compare and contrast them to OSPF. Here's what we'll cover in today's video. First, I'll give a general overview of dynamic routing protocols, to demonstrate how they function, and why they're usually preferred over static routes. There are a few types of dynamic routing protocols, so I will break them down. We will then take a brief look at dynamic routing protocol metrics. A protocol's metric is how it measures how far the destination is, like the route cost in spanning tree protocol, and it's used to determine the best route to a destination. Finally, we'll talk about something called administrative distance, which is another part of determining the best route to a destination. Stick around to the end of today's quiz for a bonus question from Boson ExSim for CCNA, the best practice exams for the CCNA, and the ones I used when I studied for my CCNA. If you want to get a copy of ExSim, follow the link in the description. Here is the network topology I'll use for the beginning of this demonstration. 4 routers, R1, R2, R3, and R4, and there is a LAN connected to R4, 192.168.4.0/24. We'll be focusing mostly on R1's perspective for now. Without configuring any static routes or dynamic routing protocol, R1's routing table looks like this, just connected and local routes, which were automatically added when IP addresses were configured on its interfaces. Let me take a minute to clarify a few points on the exam topics list. These two routes here, 10.0.12.0/30 and 10.0.13.0/30, are examples of network routes. A network route is simply a route to a network or subnet. In other words, a route with a mask length less than /32. For example, if we configure a static route to 192.168.4.0/24, that's a network route also. It's not a route to a single host, but a route to a whole subnet. These two routes, 10.0.12.1/32 and 10.0.13.1/32, are examples of host routes. A host route is a route to a specific host, a single address, specified with a /32 mask. These two routes here were automatically added, and are host routes to the specific addresses configured on R1's G00 and G10 interfaces. To configure a static route to a host, use iproute, followed by the host's address, then 255.255.255.255, which is a /32 mask. Okay, that was just an aside. so you understand those two terms. Now let's talk about dynamic routing. Instead of configuring static routes on each of these routers, we can enable a dynamic routing protocol on them. Then, R4 will advertise this 192.168.4.0/24 network to its neighbor, R2, saying, "You can reach this network via me." R2 will add that route to its route table. It will then advertise the same thing to R1, telling R1 that it can reach 192.168.4.0/24 via R2. R1 will add this route to its route table. Actually, if you look above that route, you can see that R2 also advertised the 10.0.24.0/30 network between R2 and R4 to R1, and R1 added it to its route table. R1 will then in turn advertise to R3, telling R3 that it can reach 192.168.4.0/24 via R1. It will also advertise the 10.0.24.0/30 network that it learned from R2, as well as the 10.0.12.0/30 network between R1 and R2. But we're just focusing on the one network for now. How about if there is an error and R4's G00 interface goes down? The other routers will automatically adapt and remove the route from their route tables. As you can see, R1 has removed the route. This will prevent R1 from continuously sending traffic to a dead end. What if the same situation happened when using static routing? I configured a static route on R1. It can send traffic to R4's network with no problems. However, what if the same failure on the link occurs? Because there is no dynamic routing protocol in use, R1 is unaware that it can no longer reach the 192.168.4.0 network. If it receives packets destined for that network, it will continue forwarding them to R2, unaware that R2 can no longer reach the network. Okay, so that's a benefit of dynamic routing. The router will remove invalid routes. However, we really should make sure there is a backup route, so instead of totally removing the destination network from the route table, it is replaced with the next best route. So I've added another connection between R3 and R4. Now R1 has two valid paths to R4's internal network, via R2 and via R3. Let's check R1's route table. You can see it still has the route via R2 in its route table, as it says via 10.0.12.2. In this case, what will happen if I disable R4's G00 interface to simulate a failure? So I did that, and now let's check R1's route table. As you can see, the route via R2 was now automatically replaced with the route via R3. It says via 10.0.13.2. So we lost the preferred route to 192.168.4.0, but traffic can still follow this path. Now you may be wondering, why the route via R2 was preferred over the route via R3. That's because this connection here is a fast Ethernet connection, not gigabit Ethernet. You're already familiar with the spanning tree concept of route cost, which is used to determine the best path to the route bridge. Well, dynamic routing protocols use a similar concept to determine the best path to a destination. R1 learned about the 192.168.4.0/24 network from both R2 and R3. However, it determined that the path via R2 is superior because it costs less. Okay, so that's a very quick introduction to dynamic routing protocols and their basic purpose. Here are a few key points. Routers can use dynamic routing protocols to advertise information about their connected routes, as well as routes they have learned from other devices. They form adjacencies, also known as neighbor relationships or neighborships, with adjacent routers to exchange this information. For example, in this network, R1 will form adjacencies with R2 and R3, its directly connected neighbors. If multiple routes to a destination are learned, the router determines which route is superior and adds it to the routing table. It uses the metric of the route to decide which is superior, and the lower metric is superior. Just like in spanning tree, the lower route cost is superior when determining the route port on a switch. I'll talk more about metric later. Now let's talk about the different types of dynamic routing protocols. Dynamic routing protocols can be divided into two main categories: IGP, which stands for Interior Gateway Protocol, and EGP, which stands for Exterior Gateway Protocol. Let's define those. IGPs are used to share routes within a single autonomous system, AS, which is a single organization, for example, a company. EGPs are used to share routes between different autonomous systems. Maybe this diagram will make it easier to understand. Company A, Company B, ISP A, and ISP B are each their own autonomous system, AS. Within each organization, an IGP is used to exchange routing information. However, to exchange routing information between ASs, an EGP is used. The basic purpose of IGPs and EGPs is the same, to share information about routes to destinations. However, they function differently. Because this is a CCNA course, we will focus mostly on OSPF, which is an IGP. However, you will also learn about other IGPs and the one EGP that is in use today, to the extent that you need to know them for the exam. Now let's break down these categories further. As I mentioned, the two big categories are interior gateway protocols, IGPs, and exterior gateway protocols, EGPs. However, you can further break these categories down by the algorithm type. This refers to the processes used by each protocol to share route information and determine the best route to each destination. There is only one type of EGP algorithm, path vector. Not only is there only one type of EGP algorithm, but there is only one EGP that is used in modern networks. That is BGP, the Border Gateway Protocol. Because it's not necessary for the CCNA, I won't talk much about BGP. I will mention a few important things later, but beyond that, you don't need to know BGP for the CCNA. Just make sure you're aware of the purpose of an EGP, to share route information between autonomous systems, and know that BGP is the only EGP that is used in modern networks. So, you also don't need to know the details of how a path vector algorithm functions. Now, IGPs have two algorithm types, distance vector and link state. I'll repeat, when I say algorithm, I mean the processes each protocol uses to share route information and choose the best route to each destination. All routing protocols have the same goal. That is what I just said, to share route information and select the best route to each destination. However, the algorithm used to do so is different for each routing protocol. There are two distance vector protocols, RIP, the Routing Information Protocol, and EIGRP, the Enhanced Interior Gateway Routing Protocol. I won't cover these two protocols in depth, although I will give you a basic outline of their function, so you can compare and contrast them with OSPF. So, RIP and EIGRP are the two distance vector protocols. There are also two link state protocols, OSPF, Open Shortest Path First, and ISIS, Intermediate System to Intermediate System. Like BGP, I won't talk about ISIS much. If you want to learn more about ISIS, consider looking into the CCNP service provider path after the CCNA. OSPF, however, I will spend plenty of time talking about over the next few videos. For now, what I want you to remember is, first of all, the names of each of these routing protocols. Then remember which protocols use which kind of algorithm. RIP and EIGRP use a distance vector algorithm. OSPF and ISIS use a link state algorithm, and BGP uses a path vector algorithm. The flashcards I provide will be very helpful for this. Okay, now I want to outline the characteristics of distance vector and link state protocols. I'll start with distance vector routing protocols. Once again, the distance vector protocols we will learn about are RIP and EIGRP. Distance vector protocols were invented before link state protocols, in the early 1980s. Early examples of distance vector protocols are RIP and Cisco's proprietary protocol, IGRP, which was later updated to become EIGRP. Distance vector protocols operate by sending the following information to their directly connected neighbors: their known destination networks, and their metric to reach their known destination networks. This method of sharing route information is often called routing by rumor. Why the name? It's because the router doesn't know about the network beyond its neighbors. It only knows the information that its neighbors tell it. This is different than link state routing protocols, in which the router develops a more complete picture of the network. When using a distance vector protocol, on the other hand, all the router knows is the routes its neighbor tells it about, and their metric to reach those destinations. The reason for the name distance vector is because the routers only learn the distance, which is the metric, and the vector, which is the direction to send the traffic, the next hop router, of each route. Basically, distance vector protocols work by sharing their route table, or parts of it, with their neighbors. So the example I showed you before of R4 advertising its 192.168.4.0 network is an example of distance vector logic. R4 tells R2, its directly connected neighbor, you can reach 192.168.4.0/24 via me. My metric to reach it is 1. Don't worry about the metric numbers yet. Each routing protocol uses a different type of metric, and we will cover those soon. Anyway, R2 doesn't know anything except that it can reach 192.168.4.0/24 via R4, and that R4's metric is 1. Similarly, R2 then tells R1 the same, except it advertises the metric as 2. Once again, R1 doesn't have a detailed picture of the network. All it knows is that it can reach 192.168.4.0/24 via R2, and that R2's metric to reach it is 2. And of course, R1 advertises the network to R3, with its own metric to reach the destination network. Once again, RIP and EIGRP are the two distance vector routing protocols that are used, and we will talk more about them in Day 25's video. Next, I'll briefly introduce link state routing protocols. When using a link state routing protocol, every router creates a connectivity map of the network. This map will be the same on each router. To allow this, each router advertises information about its interfaces, its connected networks, to its neighbors. These advertisements are passed along to other routers until all routers in the network develop the same map of the network. Then, each router independently uses this map to calculate the best routes to each destination. I think you can see how this is different than the routing by rumor of distance vector protocols. In link state protocols, each router gets a whole picture of the network so that it can calculate the best routes. Link state protocols use more resources, more CPU power and memory on the router, because more information is shared. However, link state protocols tend to be faster in reacting to changes in the network than distance vector protocols. The two link state protocols in use today are OSPF and ISIS. I will briefly mention some things about ISIS, but as for OSPF, we will go very in-depth. Now let's talk about those metrics that I mentioned a few times. A router's route table contains the best route to each destination network it knows about. If a router using a dynamic routing protocol learns two different routes to the same destination, how does it determine which is best? As I briefly mentioned before, it uses the metric value of the routes to determine which is best. A lower metric is considered better. It's like the root cost in spanning tree. A lower root cost is considered superior, so the interface with the lowest root cost will become the root port. For dynamic routing protocols, the route with the lowest metric is considered best and will be entered into the routing table. Each routing protocol uses a different metric to determine which route is the best. Here, in this slide I showed you before, although R1 learns two paths to 192.168.4.0/24, one via R2 and one via R3, only the route via R2 is added to the routing table. This fast Ethernet connection here has a higher metric cost than the other gigabit Ethernet connections, so this route is less favorable. Now you might be wondering, what if this was also a gigabit Ethernet connection? Both routes would have the same cost, so which route would be added to the route table? Let's see what happens. I changed the connection between R3 and R4 to be a gigabit Ethernet connection, like the others. Let's check out R1's route table. So, both routes have been added to the table, via 10.0.13.2, which is R3, and via 10.0.12.2, which is R2. So, if a router learns two or more routes via the same routing protocol to the same destination with the same metric, both will be added to the routing table. Traffic will be load balanced over both routes. Note that they must be exactly the same destination, the same network address, and same prefix length. Here's a larger view. In this case, both routes were learned by the dynamic routing protocol OSPF, as indicated by the code O next to the routes. They are both to the exact same destination, 192.168.4.0/24, and they both have the same metric. The metric value itself is also displayed in this output. Where is it? It's here. The second value in these square brackets is the metric value of the route. Both routes have a metric of 3, so both were added, and traffic will be load balanced over both routes. This is called equal cost multipath, or ECMP load balancing. Make sure you remember this term, ECMP. It will come up often in these videos about dynamic routing protocols. As for these values on the left side of the square brackets, this is another important value called administrative distance, or AD, which I will talk about a few slides later. The OSPF protocol has an AD of 110. Don't memorize that now. As I said, I'll talk about that again in a few slides. Since I just showed you ECMP, equal cost multipath load balancing with a dynamic routing protocol, I just want to let you know that you can do the same with static routes as well. I disabled OSPF on R1, and then configured two static routes to 192.168.4.0, one via R2 and one via R3. Then, both are added to the routing table, and traffic will be load balanced over both routes. Notice that both routes have a metric of 0. Static routes don't really use the concept of metric, so you'll always see 0 here. Notice also that the administrative distance, AD, value of static routes is 1. As I said, I'll talk about what AD is in a few slides. For now, let's return back to the topic of metric. As I already mentioned, each routing protocol uses a different metric. I will go into each of these in more detail in later videos, but here is a summary to introduce you to each. RIP uses by far the simplest metric, hop count. Each router in the path to the destination counts as one hop, and the total metric is the total number of hops to reach the destination. One big downside is that links of all speeds are equal. They all count as one hop. A 10 megabit per second Ethernet link is one hop, and a 10 gigabit per second link is one hop. So this is a very primitive way of calculating metric, and is clearly not ideal. EIGRP uses the most complicated metric of the IGPs, which is a calculation based on bandwidth and delay by default. However, with configuration, other factors can be calculated as well. One thing to note is that only the bandwidth of the slowest link in the route is used to calculate the metric, but the total delay values of all links in the path are used. This delay value is a little misleading, since by default it's a value assigned to the interface based on its bandwidth. Anyway, I'll talk more about this in the next video, when we go in more depth on EIGRP. Next up is OSPF. Its metric is called cost. The cost of each link is calculated based on the bandwidth, and the total bandwidth of the links in the route make up the metric of the route. This is a very simple way of calculating metric, but also clearly better than RIPs, which doesn't take into account link speed. Finally, ISIS also uses a metric called cost. However, the cost of each link is not automatically calculated based on bandwidth. All links have a cost of 10 by default. So without any configuration, it functions the same as RIP, being a simple hop count metric. Okay, so ISIS I won't talk about much, but these other three I will give more detail about in future videos. For now, just remember the basics. RIP uses hop count, EIGRP uses a calculation based on bandwidth and delay, and OSPF uses a cost based on bandwidth. The purpose of all of these metrics is the same, to let the router select the best route to the destination. To briefly demonstrate how the difference in metrics can affect which routes the router selects, let's look at this diagram again from R1's perspective, deciding which route to 192.168.4.0/24 to select for its route table. If it uses RIP, the metric is hop count. Via R2, the hop count is 2. One hop to R2, one hop to R4. Via R3, the hop count is also 2. One hop to R3, one hop to R4, even though the connection from R3 to R4 is a slower, fast Ethernet connection. So both routes will be put into R1's route table, and R1 will load balance traffic using both routes, even though one route is slower. However, if OSPF is used instead of RIP, which path will be used? Unlike RIP, OSPF's metric cost does take into account bandwidth. So the slower connection between R3 and R4 will result in a higher metric value, making it less favorable. So only this route will be entered into the route table, and R1 will send all traffic destined to the 192.168.4.0/24 network via R2. RIP views both routes as equal, but OSPF does not. Again, the purpose of all of these metrics is the same, to let the router select the best route to the destination, but some routing protocols might make better decisions than others. Now let's talk about administrative distance, which I briefly mentioned earlier. In most cases, a company will only use a single IGP for the network, usually OSPF, but sometimes EIGRP if they only use Cisco equipment. However, in some rare cases, they might use two. For example, if two companies connect their networks to share information, two different routing protocols might be in use. You might connect a network running OSPF to a network running EIGRP. Metric, which I just showed you, is used to compare routes learned via the same routing protocol. If a router learns two routes to the same destination via OSPF, it uses Metric to choose which route is better. However, different routing protocols use totally different metrics, so they cannot be compared. For example, an OSPF route to 192.168.4.0/24 might have a metric of 30, while an EIGRP route to the same destination might have a metric of 33,280. Which route is better? Which route should the router put in the route table? We can't really answer those questions by looking at the metrics, because OSPF and EIGRP use totally different metrics. So the administrative distance, or AD, is used to determine which routing protocol is preferred. A lower AD is preferred, and indicates that the routing protocol is considered more trustworthy, meaning more likely to select good routes. As you saw before, RIP's hop count-based metric system is not very good, so it has a high AD because it's not as trustworthy. It might say two routes are equal because they have the same hop count, although really one route is much worse because of lower bandwidth. Ready for some memorization? These are the administrative distances of most common types of routes. I highly recommend you use the flashcards to remember these. I would be surprised if you don't get a question on the exam like, two routes to the 10.0.0.0/24 network are learned, one from OSPF and one from EIGRP. Which route will be entered in the route table? To answer that question, you would need to know that EIGRP has a lower AD, so the EIGRP route is preferred and will be entered in the route table. Again, a lower AD number is preferred and will be selected over a higher AD. Keep in mind that these are the values used on Cisco devices. Other vendors might rank these differently. So, the most preferred routes are those to directly connected networks. They have an AD of 0. Static routes are the next best. They have an AD of 1. Next up are external BGP, also known as eBGP routes, with an AD of 20. There is another kind of BGP, internal BGP, IBGP, which you'll see later. EIGRP routes have an AD of 90. Next is IGRP, the older version of EIGRP, with an AD of 100. OSPF has an AD of 110. ISIS has an AD of 115, and RIP has an AD of 120. So, of the IGPs I showed you, which are RIP, EIGRP, OSPF, and ISIS, EIGRP is the most preferred. It has the lowest AD. However, EIGRP external routes have a higher AD, 170. These are beyond the scope of the CCNA. But basically, they are routes from outside of the EIGRP network that are then advertised into EIGRP. Then, internal BGP, IBGP, has an AD of 200. Then one more. Routes with an AD of 255 are unusable. Here's a quote from Cisco. If the administrative distance is 255, the router does not believe the source of that route and does not install the route in the routing table. So, make sure you memorize these. If you're not using the flashcards, I really think you should for things like this. Without flashcards, it might be difficult to memorize these. But if you use the flashcards, it's quite easy. Here's a quick quiz question to demonstrate a point. The following routes to the destination network 10.1.1.0/24 are learned. A route with a next hop of 192.168.1.1 learned via RIP with a metric of 5. a route with a next hop of 192.168.2.1, learned via RIP, with a metric of 3, and a route with a next hop of 192.168.3.1, learned via OSPF, with a metric of 10. Which route to 10.1.1.0/24 will be added to the route table? Pause the video to think about the answer. Okay, so the answer is the OSPF route will be added to the route table. Metric is used to compare routes learned from the same routing protocol. However, before comparing metrics, AD is used to select the best route. The OSPF route will always take precedence over the RIP routes because it has a lower AD. Looking back at the route table I showed you before, here you can see the AD of 1 for these static routes. The connected and local routes above them have an AD of 0, but it is not displayed in the route table. And another look at this route table with OSPF routes. Here you can see the AD of 110. Remember that the number on the left inside the square brackets is the AD, and the number on the right is the metric. One final point before moving on to the quiz. You can change the AD of a routing protocol, and I will demonstrate this when we cover OSPF configuration in a later video. If you want OSPF routes to be preferred over EIGRP routes, you can configure the router to do that. You can also change the AD of a static route. Notice here I use the standard command to configure a static route. IP route, followed by the destination, the subnet mask, and then the next hop address. However, I use the question mark to check for further options. Here it says distance metric for this route. It includes the word metric, but don't confuse this for the metric we talked about earlier. This is administrative distance. So I configured the route with an AD of 100. In the output of show IP route, you can see that the AD is now 100 instead of the default 1 for a normal static route. Now, why would you want to do this? By changing the AD of a static route, you can make it less preferred than routes learned by a dynamic routing protocol to the same destination. But you have to make sure that the static route's AD is higher than the routing protocol's AD, or else the static route will still be preferred. This kind of static route is called a floating static route. The route will be inactive, meaning it won't be in the routing table, unless the route learned by the dynamic routing protocol is removed. For example, maybe the remote router stops advertising it for some reason, or an interface failure causes an adjacency with a neighbor to be lost. You can see here that floating static routes are part of the exam topics list. Make sure to watch the lab videos and download my Packet Tracer labs to get practice configuring everything we cover. Okay, so let's quickly review what we covered in today's video. I gave you a brief introduction to dynamic routing protocols. They allow routers to automatically learn routes to different destinations without having to manually configure static routes. Static routes are useful, but in large networks, it's not practical to use only static routes. You would have to configure thousands of different routes, which is not a good strategy. We covered the different types of dynamic routing protocols. First, the big two categories are IGPs, interior gateway protocols, used for routing within an organization. Then there are EGPs, exterior gateway protocols, used for routing between organizations, for example, over the internet. The only EGP in use these days is BGP. We can also categorize routing protocols by the kind of algorithm they use. There's one type of EGP algorithm, that is path vector. However, there are two different kinds of IGP algorithms. Distance vector, used by RIP and EIGRP, also link state, used by OSPF and ISIS. Then we talked about metrics. Each routing protocol uses a different metric, which is a value used to determine the best route to a destination within the same routing protocol. However, how do you compare different routing protocols? With administrative distance. Use the flashcards to remember the AD of each kind of route and routing protocol. I'm sure you'll need it for the test. I introduced a lot of topics in this video, so I want to say that you shouldn't be worried if you feel you don't understand completely yet. In the next video, I will cover RIP and EIGRP, and then the next 2 or 3 videos after that will cover OSPF. In those videos, we will review all of these fundamental topics again, such as administrative distance and metric. Okay, let's move on to today's quiz. At the end of the quiz, there will be a bonus question from Boson ExSim, the best practice exams for the CCNA. If you're preparing for the CCNA exam and you want to make sure you're really ready, Boson ExSim is, in my opinion, the single best thing you can get to prepare yourself for the real exam. Follow the link in the description to get Boson ExSim. Here's quiz question 1. R1 learns 4 routes to 192.168.1.0/24 through multiple routing protocols: RIP, EIGRP, OSPF, and ISIS. Which route or routes will be added to the route table? A. The RIP route only. B. The EIGRP route only. C. The OSPF route only. D. The ISIS route only. E. The RIP and EIGRP routes, because both are distance vector protocols. F. OSPF and ISIS, because both are link state protocols. Or G. All routes will be added to the routing table. Pause the video to think about your answer. The answer is B. Only the EIGRP route will be added to the routing table. Why is this? When selecting which route to a certain destination to add to the routing table, and routes are learned from multiple routing protocols, the AD is used to determine which will be added to the routing table. EIGRP has the lowest AD of the 4 protocols, so only the EIGRP route will be added to the routing table. Let's go to question 2. Which type of routing protocol is also known as routing by rumor? A. Link state. B. Path vector. C. Distance vector. Or D. Interior gateway. Pause the video to think about your answer. The answer is C. Distance vector. Distance vector protocols such as RIP and EIGRP operate by telling neighboring routers which routes they know and their metrics to reach those networks. This is known as routing by rumor. A is incorrect because when using a link state protocol such as ISIS or OSPF, each router develops a complete map of the network to calculate the best routes, which is different than the minimal information a router receives from neighbors when using a distance vector protocol. B, path vector, is a type of EGP, exterior gateway protocol. It's not covered in the current CCNA and operates differently than distance vector. D, interior gateway protocols, or IGP, is a category which includes both distance vector and link state protocols, so it is incorrect. Let's go to question 3. R1 learns 2 routes to 172.16.0.0/16 via RIP, one via 10.0.0.1 and the other via 10.1.0.1. Both routes are 5 hops away. Which route or routes will be entered into the routing table? A. Both routes. B. Only the route via 10.0.0.1. C. Only the route via 10.1.0.1. Or D. Neither route will be added because RIP's AD value is too high. Pause the video to think about your answer. The answer is A. Both routes will be added to the route table. Both routes are to the same destination, 172.16.0.0/16. They were learned through the same protocol, RIP, and they have the same metric, 5. So because of these conditions, both will be added to the routing table, and R1 will load balance traffic over the 2 routes. As for option D, if R1 also learned a route to 172.16.0.0/16 via another routing protocol such as OSPF, this would be true, because RIP's AD value is higher than OSPF, so it is less preferred. However, there was no mention of another routing protocol, so D is incorrect. Okay, now let's take a look at a bonus question from Boson ExSim for CCNA. Okay, for today's Boson ExSim practice question, I got another question that I really like. It's a good question about route selection. Let's get right into it. You issue the show IP route command on router A and receive the following partial output. So we are shown 4 routes, S, R, D, O. S is a static route, R is learned via RIP, D is learned via EIGRP, that's right, it's D, not E, and O is OSPF. So they are to 4 different destinations. All of them begin 10.20.0.0, but they have different prefix lengths, so these all count as different destinations. The static route is /22, /24, /26, /28. So these are not the same destination. So that's why, even though the static route has the lowest AD, it's the most preferred, all of the routes appear in the routing table, not just the static route. So router A receives a packet that is destined for 10.20.0.14. Which of the following routes will router A use to send the packet? Select the best answer. So A, the RIP route, because it has the highest administrative distance. B, the OSPF route, because it is the route with the longest prefix match. C, the static route, because static routes are preferred over dynamic routes. Or D, the EIGRP route, because it has the lowest administrative distance. Okay, pause the video here to think about your answer. Okay, so let's check the answer. So in today's video, I just talked about metric and administrative distance. So if you receive routes from multiple routing protocols to the same destination, you use the administrative distance to select the route. But if you get multiple routes from the same routing protocol, you use the metric. However, these routes are not to the same destination. These are different destinations, as I just said, because the prefix lengths are different. So these AD and metric numbers are irrelevant. So what did I tell you in, I believe it was day 11's video about static routes? How does the router decide which route to use if this destination matches multiple entries in the routing table? And this destination does match all of these entries, so it could use any route. Which one does it use? It uses the most specific match. And most specific means the longest prefix. So that is /28. So it should use this OSPF route and send the packet to 192.168.10.1 out of its serial 01 interface. So I think B, the OSPF route, because it is the route with the longest prefix match, is the correct answer. Let's check. And it is. So if you didn't quite understand my explanation, here is Boson's explanation. You can pause the video here to read it. This is the great thing about Boson ExSim is it gives you in detail explanations, not just why B is correct, but also why A, C, and D are incorrect. And after that, there's a reference to some Cisco documentation, which is freely available on the internet, route selection in Cisco routers. Okay, so that was today's Boson ExSim practice question. If you want to get a copy of ExSim, please follow the link in the video description. These are the exams I used when I studied for my CCNA and CCNP exams, and I really think they helped me pass all of my exams on the first try. So once again, if you want to get a copy of ExSim, please follow the link in the video description. There are supplementary materials for this video. There is a flashcard deck to use with the software Anki. There will also be a packet tracer practice lab so you can get some hands-on practice. That will be in the next video. Sign up for my mailing list via the link in the description, and I'll send you all of the flashcards and packet tracer lab files for the course. Before finishing today's video, I want to thank my JCNP level channel members. Thank you to John, Funny Dart, Joshua, Scott, Alexa, Hassan, Gerard, TB, Vikram, Joyce, Marek, Samil, Velvijaykum, C-Mode, Johan, Mark, Miguel, Yusuf, Kone, Boson Software, the creators of ExSim, CD, Magrathia, Devin, Charlesetta, Lito, Jonathan, Mike, Alexander, and Vance. Sorry if I pronounced your name incorrectly, but thank you so much for your support. One of you is still displaying as channel failed to load. If this is you, please let me know and I'll see if YouTube can fix it. This is the list of JCNP level members at the time of recording, by the way, June 13th, 2020. If you signed up recently and your name isn't on here, don't worry, you'll be in future videos. Thank you for watching. Please subscribe to the channel, like the video, leave a comment, and share the video with anyone else studying for the CCNA. If you want to leave a tip, check the links in the description. I'm also a Brave verified publisher and accept BAT or Basic Attention Token tips via the Brave browser. That's all for now.